All right, we're going to continue with section 4.2, inverse functions. We started this in class, so if you were absent, you need to, before you watch the video, you need to go through the PowerPoint that we did in class. I've posted that on Blackboard, and familiarize yourself with that before watching the video. The first two learning targets that I have listed here are the ones that we did in class. So if you were in class, you should already have those written down. The third learning target, the red one, is the one that you should write down now, the one we're going to talk about in this video. Be able to find the inverse of a function using its equation. Before we get into that third one, let's go ahead and just do a little refresher on what we did in class. So first we said let f denote a one-to-one function, and we talked about how it is important that when we are finding inverses that our original function is one-to-one. If it is not one-to-one, once we take the inverse, then we will no longer have a function. So the function cannot be a many-to-one function, because when we invert it, the inverse would not be a function. So starting with a function that is always one-to-one, then the inverse is denoted f inverse of x. So when we have that -1 raised to the -1 exponent there, that means we read this f inverse of x. So that is just the notation that you use to say it is the inverse. So we can verify that two equations are inverses of each other if we compose them together. So if I take the inverse of the function and plug it into the original function, I should get x as my answer. And if I take the original function and plug it into the inverse, I should also get x. This is because the functions are reflections. They're reflected over the line y equals x. Okay, they're reflections of each other. So when we compose them together, we should get that answer of x. So I'm going to start by doing f of g of x. So I'm going to take g of x and I'm going to plug it in for x into my f function. So 2 times 1/2 x minus 3 plus 6. So I just replace my x with 1/2 x minus 3. Simplify this. 2 times 1/2 x is 1x. 2 times -3 is -6. And then I have plus 6. So I get x when I compose those together. But they're only inverses of each other if you get x if you go both ways. So I need to also check g of f of x. So I'm going to take f of x, I'm going to plug it in for x in my g equation. So 1/2, and I'm going to replace my x with 2x plus 6 minus 3 on the outside. Distribute that 1/2. 1/2 times 2x is 1x. 1/2 times 6 is 3. And I get x. So if I compose the two equations together both ways, and I get x both times, this means f of x and g of x are inverses of each other. So if it ever asks you to verify that two equations are inverses of each other, you'll need to plug them in both ways to see if you get x. All right, so a little also refresher from what we did in class today. I'm just going to go through this really quickly again. So if you look at, I want you to start by looking at our first function here. F of x is equal to x squared plus 9 over 2. And we have specified that x has to be greater than or equal to 0. So if you're looking at this blue function over here, this blue graph, the domain of it goes from 0 to infinity because x had to be greater than or equal to 0. Okay, so this should be a bracket here. and the range starts at 4.5 and goes to infinity. So it can be 4.5 to infinity for the range. Now let's take a look at the inverse of that function. So here's the equation for the inverse, and the graph of that will be the green one over here on the right. So you'll notice that the domain, now the x value starts at 4.5 and goes to infinity. And the range, your y values start at 0 and go to infinity. So what do we notice? So you can see that the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. So you can see that. Let's look at the second example. So we have our original function, f of x equals 2x plus 3 over x minus 4. So the blue graph over here is what you'll be looking at for that first function. So my domain, the x values, we have a vertical asymptote at 4, which means our domain is going to go from negative infinity to 4, and then from 4 to infinity. If we're looking at the range, so all the y values, we can see here that we have a horizontal asymptote at 2 that the graph doesn't ever cross. So our range goes from negative infinity to 2 and from 2 to infinity. So now let's look at the inverse function. We have 4x plus 3 over x minus 2. It's this green graph over here on the right that you're looking at. So for this one, it looks like we have a vertical asymptote at 2. So our domain goes from negative infinity to 2 and from 2 to infinity. We also have a horizontal asymptote at 4. So the range goes from negative infinity to 4 and from 4 to infinity. So again, our domain of our original became the range of our inverse, and the range of our original function becomes the domain of our inverse. So we talked about this a little bit, about this is because, again, that it reflects over the line y equals x. Because if I have this point here, if I have 2, 5 as a point on my original graph, then I should have 5, 2, 7. 2, 7. Then I should have 7, 2 as a point on my inverse. Here I have, it looks like 4, 13 on the original graph. So 13, 4 should be on my inverse. So all of the x values of the original become all of the y values of the inverse. All the y values of the original become the x values of the inverse. Okay, so the domain is f of f is equal to the range of f inverse and vice versa. All right, so let's do an example where we're trying to find the inverse using just the equation. So we're going to start by looking at that first function that we just looked at the domain and range of, and given just the equation, we want to be able to find the inverse. So the big key that we're going to use for inverses always is that the domain and range flip-flop. Okay. The domain of the original becomes the range of the inverse and vice versa, which means all the x values of the original become all the y values of the inverse. And all the y values of the original become the x values of the inverse. So I'm going to rewrite this. We know that f of x is interchangeable with y. This f of x denotes my y output. So we know that in inverses, my y values and my x values are going to be flip-flopped. So I can just switch my x and my y's in the equation as well. Simple as that. Now we just want to put it in function form. So we want our answer to actually look like a function. So instead of keeping it as x equals y squared plus 9 over 2, we want to solve for y so that we can get the equation into a function form so that we'd be able to graph it from there. So multiply by 2 on both sides. Cancel out that 2. 2x is equal to y squared plus 9. Subtract 9 on both sides. 2x minus 9 equals y squared. Take the square root of both sides, and y is equal to the square root of 2x minus 9. Here's the question that you may be asking yourself. Do I need to put a positive negative in front of that square root since I took the square root of both sides? So let's take a look at our calculator really quick. And I'm going to graph the positive square root of 2x minus 9. Oops. And the negative square root of 2x minus 9. So that would be, this would be the graph if I had both positive and negative square root of 2x minus 9 as my equation. And I graph that, what happens? So when we graph that, what we get is an equation that does not pass the vertical line test. So this is not a function. And when we take the inverse, we need the inverse to also be a function. So this is why up here we were clear that x had to be greater than or equal to 0, because this is the domain which will become the range. And so if we only look at the part of the graph where y is greater than or equal to 0, then that is a function. So we would not use positive and negative, we would only want the positive. So your answer is going to be f inverse of x is equal to just the square root of 2x minus 9. So that our domain and ranges match. When you are giving your answer, you must write it in inverse notation. So I need to see not y equals, but f inverse of x is equal to the square root of 2x minus 9. All right, let's do another example. So we have the inverse of f of x is equal to 2x plus 3 over x minus 4. And over here, we're defining the domain. We're saying that x can't be equal to 4. Because if I were to plug 4 in for x, I would get 0 in the denominator, and that wouldn't be possible. So we're just saying we need the inverse of this function where x cannot be equal to 4. So we're going to write this as y equals 2x plus 3 over x minus 4. And we're going to flip-flop. Anywhere you see a y, you plug in an x. And anywhere you see an x, you plug in a y. So we're going to have x equals 2y plus 3 over y minus 4. So just flip-flopping those x and y's. Then we need to solve for y so that it's in a function form. So solving for y, I'm going to multiply by y minus 4 on both sides to clear this denominator. So these cancel out, and I get x times y minus 4 is equal to 2y plus 3. Okay, trying to get x by itself. I'm sorry, trying to get y by itself. Let's go ahead and distribute this. So xy minus 4x is equal to 2y plus 3. So we need to get all of our y's together on one side and everything else on the other side. So I'm going to add the 4x to both sides here. And I'm going to subtract my 2y so that I get xy minus 2y is equal to 3 plus 4x. All right. So again, trying to get the y's all just on one side. So what do you notice about the left side of this equation? What could you do to simplify that left side of the equation? Because I need just my y's together and everything else taken away. So on this left side of the equation, we have a greatest common factor of y. So I'm going to take out the y. Let's go ahead and put this in standard form. 4x plus 3. So I take out my y, and now I can just divide by x minus 2 on both sides to get y by itself. So I get y is equal to 4x plus 3 over x minus 2. Okay. So f inverse of x is equal to 4x plus 3 over x minus 2. All right. Last example, we're going to find the inverse of f of x. So we have x squared plus 3 over 3x squared. Again, where x has to be greater than 0, because if it was anything less than 0, when we took the inverse of it, we would not get a function. So our domain has to be greater than 0 so that my range of the inverse is also greater than 0. Okay, so first part, find the inverse of f of x. Then, do it this way. Then we're going to find the range of f using the inverse. So we already know that the domain of this function f is from 0 to infinity. But we don't know what the range is. We will find the range of f using the inverse once I find it. All right. So let's find the inverse. I have y equals x squared plus 3 over 3x squared. So flip-flopping my x and y's. X equals y squared plus 3 over 3y squared. Let's solve for x. Multiply by 3y squared on both sides. And I get 3xy squared is equal to, these cancel out, y squared plus 3. All right, so I need all my y's together on one side. So I'm going to subtract y squared, and I get 3xy squared minus y squared is equal to 3. Same sort of deal going on with this left side of the equation. You'll notice that that left side of the equation has a y squared as its greatest common factor, and y is what we're trying to solve for. So take out that y squared, and we have 3x minus 1. Okay. Let's rewrite this up here. Y squared times 3x minus 1 equals 3. Divide by 3x minus 1. And you get y squared is equal to 3 over 3x minus 1. Take the square root of both sides. Y equals the square root of 3 over the square root of 3x minus 1. Now remember a couple of things. One, we're not going to do positive and negative because otherwise we would not have a function. Because our range has to be greater than 0. Also, I cannot have a square root in the denominator. So I'm going to multiply this by the square root of 3x plus 1 on the top and the bottom to clear that denominator, or to clear that square root in the denominator. So I have the square root of 9x plus 3 over the square root of let's see right quick. So we have 9x squared plus 3x minus 3x minus 1. Okay. The bottom is a difference of perfect squares. Hold on, it's not working out so well. You know what? Let's pause there for a second. Okay, there's something that I think I'm missing in there that I need to look back at really quick. So go ahead and pause there in your notes. Okay. And we're going to keep this as y equals the square root of 3 over 3x minus 1 for now. Okay? We're going to come back to that in class. So let's talk about the range of f. The range of f is equal to the domain of f inverse. So the domain of this, we have the square root of 3x minus 1 in the denominator. We rewrite this as square root of 3 over square root of 3x minus 1. So we have the square root of 3x minus 1 in the denominator. So what that means is that 3x minus 1 has to be greater than 0. So I can't take the square root of a negative. So 3x has to be greater than 1, divide by 3. X has to be greater than 1/3. So if the domain of f inverse is anything greater than 1/3, then the range of f is going to be anything greater than 1/3. Because the domain of f inverse is the same as the range of f. Okay. So pause on that. equation. We're going to come back to that equation in class next time. But here are some optional practice problems for you to do if you feel like you need a little bit more practice. 1 second. All right, sorry about that. So practice these problems, 37, 51, 63, 67. You can do all of them, or you can look at them, pick and choose, and see which ones you think you need a little bit more practice with before coming to class next time.